We're now going to begin looking at organic reactions. When we look at reactions in organic chemistry, there's a lot going on. We have very complex molecules, and because of that, we can have very complex mechanisms as to how these reactions proceed. But by understanding the mechanism, which is the actual physical way something happens, we're going to be able to predict and create organic reactions. The two types we're going to study in this unit are substitution and elimination, and both of these have two versions of how they proceed. In a substitution reaction, we're going to have some functional group on some organic molecule that gets replaced by another functional group. So you can see in this reaction, I've got a hydroxyl group with hydrobromic acid, and that hydroxyl group gets replaced by the bromide ion, resulting in water. In an elimination reaction, instead of having something replaced, I'm going to lose something. In this reaction, I'm going to be losing a hydrogen off of this carbon right here and a hydrogen off of this carbon right here to an NH2-, creating a double bond and some ammonia. I have two ways elimination reactions can happen and two ways substitution reactions can happen. And we're going to investigate both of those. Well, all four of those. But in order to investigate that, there's some vocabulary we need to learn, because we're going to be able to make a flowchart that will allow us to easily identify which type of reaction is going to occur. Sometimes there will be multiples of each type. However, in order to understand this flowchart, we're going to need to learn some new vocabulary terms. We're going to need to be able to describe how good is this functional group at leaving. How strong is this ion at pulling that carbon's attention? How easy is it to get to this carbon? These are all ideas that we need to be able to investigate. So let's start by looking at the flowchart. And I warn you, it's going to be overwhelming at first. And let's pick apart each portion of that flowchart and understand them one at a time. Looking at this flowchart, it is clearly overwhelming. It's very busy. There's a lot going on. But I want to draw your attention to the parts in red. This is the first choice we're going to be making when we look at an organic reaction. And it is referring to something called the substrate. We've already examined this property. It's called steric hindrance. Now we're going to be able to look at a way to measure how much steric hindrance is occurring. So let's move away from this flowchart. I've already got this part written out, but we're just going to start by looking at this concept of the substrate and how hindered is it. If we look back at our reaction examples here, our substrate is going to be the reactant that is the main organic molecule. This is the location where the reaction is going to happen. You could think of it like a TIE fighter docking into the Death Star. The Death Star is the substrate. The TIE fighter is the thing that is attacking the substrate. It's a bad example for a TIE fighter. But we're going to be having this molecule attack this molecule. The reaction is going to be happening from here to here, all right? So this is our substrate. This is where things are happening. Our main organic molecule is our substrate. And we need to be able to identify how much steric hindrance is occurring on that substrate, all right? So the substrate in each of these reactions is this right here. The carbon where the business is all happening, that's going to be this carbon right here. On both of these. And the way we're going to be measuring the steric hindrance is we're going to look at how many other carbons is that carbon attached to. We're always going to be attacking a carbon in these reactions. So this is a carbon, this is a carbon. Besides this functional group, which we call the leaving group, besides this leaving group, what else is this carbon attached to? Well, it's attached to one carbon here, a second carbon here, and then it's attached to a hidden hydrogen. What about this one? This one is attached to one carbon here, a second carbon here, and a third carbon here, as well as that hidden hydrogen, which is the thing that is being taken away. This NH2 minus is going to pull that hydrogen away. And so we would say 1, 2, 3. This would be 3 degrees of steric hindrance. This is 1, 2. This would be 2 degrees of steric hindrance. So we call these methyl, primary, secondary, and tertiary. Let's write those down. So we've got names here. Now let's draw 4 examples of what these would look like. So a methyl substrate. A methyl substrate is just going to be a CH3 with some kind of functional group on it. It doesn't matter what that functional group is. In any case, if that carbon is attached to that functional group, like OH, this is what we're going to use. We're going to use a hydroxyl group in each example here. If it's attached to an OH, that's really easy to get access to. So another atom, let's say we've just got a lone chlorine atom, and this is going to be the thing that's attacking. It's really easy for that to get at that OH group. It's really easy for it to hit that bond right there. That's where it's going to need to hit. So that is going to be the least hindered, all right? So our hindrance, our steric hindrance, is going to be increasing as we go down this list. So as we go down, we're going to have more hindrance. So it's going to be more hindered from being able, oh, you can't see that. So as we go down, we're going to have more hindrance. It's going to be more hindered from being able to react. All right? Next, we have a primary group. Now, a primary group is just going to be connected to one other carbon. So I've got something like, we're going to be using propanes for this. So I've got 3 carbons here, and this is the carbon right here. That guy right there, that's what's being attacked. This is the carbon that is attached to that functional group. So if I look at it this way, it would look like this. If I use a model, it looks something like this. So I can see it's pretty easy to access this little red oxygen here. It's a little more difficult than the methyl substrate because this is pretty hindered from this side. From the back end, if this chlorine was coming in this way, it would probably get deflected as it tried to come in. Versus this one, coming from the back way, it could still pretty easily hit that. It's less hindered. But regardless, both of these, from the front, from the side, easy to get in. Easy for that attacking nucleophile to get in. So next, let's look at a secondary. A secondary, using the same propane again, would have connections to 2 carbons. So again, I'm looking at this carbon to get my rating for the substrate. Steric hindrance is going to be more because it's in the middle. It's being guarded from this side and this side. So I can see that in this molecule. We can make these. You can make these with these sets. Nice and simple. I can see that this model has more defense around that oxygen atom. It is harder to get in there. Okay? So it's more steric hindrance. Finally, a tertiary. A tertiary. That would look like this, where I've got my 2 carbons, I've got my OH group, and then I'm going to have 1 more carbon hanging off to the side. So this is, again, the carbon that we're looking at. This is the carbon where all the action is happening. But that carbon is guarded all over the place. It is very difficult to get in there. So it is connected to 3 other carbons that would look like this. It would have a lot going on. It's very busy. This would be tertiary. So whenever you're looking at how much steric hindrance is occurring, you're looking at how many carbons is that one carbon that I'm looking at attached to? It does not matter how long the chains coming off of it are. Doesn't matter. So primary, I could have this group, and it would still be a primary carbon. Likewise, I could have this group. That would still be a secondary. Doesn't matter how long that chain is. And then a tertiary, I could have these huge, huge chains coming off of this. Does not matter. That is still a tertiary. We're not going to rate any more specifically than that. Even if this had something like this going on, where there are all of these extras, we're only going to be focused on that one carbon where the reaction is happening. Clear?